Behold, a great and mysterious first order differential equation. I told you it wasn't that complicated. So a differential equation is an equation that has a d something by d something in it. In this case, dy by dx. That's the rate of change of y with respect to x. And I know that dy by dx is telling me that x is the variable in this expression. And I know that I can undo differentiating by integrating. So if I want a formula for y, whatever y is, I just need to integrate. So I'm going to increase the power by 1, divide by the new power. And remember that I've got a plus c in there. We call this a differential equation, and we call this a general solution to the differential equation. We have undone the differentiating. It would be nice if I could work out the value of c, and normally we do that with a pair of values, don't we? Normally we're in the context of a graph, so we'd have a coordinate, but in these sorts of problems, often you are just given a pair of values like that. We call that a boundary condition. I substitute that in.
By the end of the day, just to kind of, like I said, you're going to have to bring the old corner back.
I'll call
8 is the same as 24 thirds, so when I take away 5 thirds, I get 19 thirds. So I now know what c is, so I can rewrite my general solution.
Don't you know these like?
So the two phrases, general solution and what we've got here, which is referred to as a particular solution, yes. Boundary condition, I'm not sure you need to know that. So a particular solution is a solution without any missing values, apart from the variables themselves. So we've worked out the value of any constants. So a differential equation is just an equation with d something by d something in, and we know it's not always dy by dx, dh by dt, dv by dw, whatever. And integrating gives us a general solution, substituting some values in gives us a particular solution. So where's the difficulty, you say? Well, unfortunately, yeah, you'll never get a question like that. First order, well, this is dy by dx, not d2y by dx squared. If it was d2y by dx squared and I wanted to get y equals, I'd have to integrate twice. That would be a second order differential equation. We don't do those. Some of you will meet those at university if you do anything mathematical. Okay, so why are we bothering with this? There's nothing new there. Okay. I'll just draw on my forehead. Here's another differential equation. This presents us with a bit of a problem, because dy by dx is telling me that x should be the variable, but y is the variable. I can't integrate this with respect to x because there's no x's to be seen, and y isn't a constant. It's not going to become 3yx. But I've got a little trick up my sleeve, haven't I? We've made it before. Because I can flip it. And if I integrate that with respect to y is the variable, I get an x equals equation. 1 over 3y becomes the log of 3y divided by what you get when you differentiate the brackets. That's my general solution. I'd be in trouble if they said writing it in the form y equals. Well, I wouldn't be in trouble. I'd have to do a little bit of log manipulation. But if they don't say that, we can leave it in that form, there's no problem. So that's my general solution this time. And go on, if I give you a boundary condition, do you want to work out a particular solution for me? Remembered at this point that log of 1, ln of 1 is 0. I promise you will have done by the end of the next couple of lessons. And so I've got a particular solution. Well, that's all nice and easy, isn't it? So how about this one? So this is the sort of problem we're going to actually face. It's a differential equation, it's a first order differential equation, but we've got a bit of a problem because it hasn't just got x, hasn't just got y, it's got x and y. So we're talking about something whose rate of change is affected by the two variables in the situation, which is perfectly possible. So how do we approach it? Well, we do a little bit of a neat trick because we this sort of statement here is a way of saying the way that y is changing with respect to x is the variable, it's the sort of the independent variable in this situation. But what we do is we do something we haven't done so far, and we do a little bit of algebra with it. So I'm going to multiply both sides by dx. And I'm going to divide both sides by tan y. So what I've effectively done is I've collected all the y stuff on one side and all the x stuff on the other side, including separating the dy by dx. And what I can now do is two separate integration sums. On this side, it's an integration with respect to y. Y is my variable, and 1 over tan is cot. And you'll find how to integrate cot on the formula sheet. So that's going to be something to do with y. On this side, I'm integrating x with respect to x, so that's all good. I'm going to increase the power, divide by the new power. So do you just want to integrate both of those things? You'll have to turn to your formula book on page 7 to remind yourself how to integrate cot. It's just cot y, there's no k involved, so it's nice and easy. Now I've done two completely separate integrations. So really I should have two completely separate constants, a plus c here and plus something else over here. But what I can do is combine the two. There's no point writing two separate constants. I can just take one away and So what we do is we just write a single constant, which is the two separate constants combined. And that is my general solution. We call this process separating the variables. So the process I went through, starting here to get to here, that's separating the variables. And actually, we're going to tomorrow revisit this problem and solve this by separating the variables instead of flipping it. So with any differential equation where the variable is not just this letter, we use this approach, separating the variables. So we've got to a general solution. So why don't we now take a boundary condition to work out a particular solution? So let's make sure we're in radians. Let's make y equal to pi over 2 and x equal to 2. So we want to get for c. So sine of pi over 2 is 1, ln of 1 is 0, 2 squared is 4, over 2 is 2, so c is minus 2. So my particular solution is now, we have a slight issue which we need to address at this point. It's not an issue which was a problem here, but when we integrate something and get an ln, we always put these modulus signs here because you can't modulus something negative. If I'd given you a different boundary condition, for example, so the sine of minus pi over 2 is minus 1. But because of the modulus signs, we just say that's ln of 1, and we would get 0 and we get the same answer. That might not be right. We can't, we've got a different set of boundary conditions, so surely we should get a different constant. So if, when you come to substitute in values, it involves the use of the modulus signs to turn a negative to a positive, you've got to think, oh, hang on a minute, I need to be careful here. And there is an alternative approach. So I'm not going to use those. I'm going to stick with this boundary condition, but I'm going to do things slightly differently. So I'm going to get to here, my general solution. And I'm going to, before I substitute in, I'm going to do a bit more work. So I'm going to e both sides, which is the inverse of ln, isn't it? I'm going to do e to the power of both sides, which on this side just gives me sine y, no longer with a modulus sign to worry about. It undoes that. I can work out the sign of anything, positive or negative, so I no longer need the modulus. That's not a 0, that's just e to the power of. On this side, I get e to the power of. I have to do that as a single e to the power of. It's not the same as e to the power of x squared over 2 plus e to the power of c. In fact, what it is on the right-hand side, well, when I multiply powers of the same thing, I add the indices. So what I've actually got here is that. That means the same as that, and that's a really crucial step in understanding a lot of the questions we're going to be doing over the next couple of lessons. Now, I've got no modulus signs. I've got rid of the ln. Let's now apply our boundary condition. Same boundary condition as before. And because my general solution, this is still my general solution, has got e to the power of c, and I don't actually need to work out what c is. I can just work out what e to the power of c is, because I don't want to have anything with an unknown value. So I only really need to know what e to the power of c is. So the sine of pi over 2 is 1. That's e squared. And that's all I want. I'm not bothered about c. I just want to know what the thing with the constant is. Now I could write that as e to the minus 2, or I could leave it as it is and rewrite my general solution. Are we happy that that multiplied by that is the same as this? Okay, what I've done is I've done e to the x squared over 2 multiplied by 1 over e squared, because that's what e to the c is, and then I just combine them. That's my particular solution. Now we've got two particular solutions now. We've got this and this. Which one is correct? Well, the answer is they're both correct. I mean, if I take this one and e both sides, here I've got a power where I'm subtracting, and I know that comes when you divide powers of the same thing. So that's which is exactly the same as we've got over there. So these two approaches give us the same answer. And if we never have to deal with a negative value inside those modulus signs with a log, we can use either. But if we encounter that issue there, we've got to take the steps that we've taken over here to avoid that negative problem. And I realise it's tough to get your head around, so I tend to do this all the time. This is only a problem in questions with logs, and they don't always involve logs, but it's a problem when you've got those ln with modular signs.
So you only do it when there would be a minus in the...
That's correct, yes,
Okay.
yeah. Well, no, it works regardless.
Yeah.
So both ways give you, but you need to do it when there's a
definitely.
minus. Yeah. So if we have a look at page 324, question 3. Page 324, question 3. I have to say, differential equations, it's really hard. All right, I'm not going to sugarcoat it. It's really hard. You're very fortunate to be the second class that I've done this with, because I've ironed out all the mistakes. Well, hopefully, the mistakes I made, not anyone else's mistakes. So, page 324, question 3 looks like this. And if you're looking in the book, they give you a little hint. Start by factorising the right-hand side, writing it as y, open brackets, 1 plus x, close brackets. And then see if you can separate the variables. Try and get everything with a y on one side and everything with an x on the other side. You're lucky in this one because you're going to get two things divided by one thing on the x side, which you can split into two separate fractions. So when the y comes down here and there's nothing left there, that's going to be 1 over y. So this is going to become ln y. That I'm going to increase the power by 1 divided by the new power. That's going to become ln x. Don't forget the plus c. So if you can get to that point, see if you can get to your general solution. So the y, when I divided both sides by y, we didn't really have anything left here, well, unless you'd move the x squared last. So that becomes 1 over y. X squared comes down here. Separate that, because it's two things over one thing, which you can do without having to worry about partial fractions. Increased power, divide by the new power. I'm going to write that as minus 1 over x. That's what it is. General solution. There are two problems with this general solution. Problem 1, they want it in the form y equals. Problem 2, when I substitute in my boundary condition values, x is minus 1, I've got the problem of a minus value which I would have to make positive, and that's potentially going to cause me an issue. So we need to E this one. But before we do, I'm going to suggest something which is optional, but certainly makes things a whole lot easier. And I'm all for making things as easy as they can be. It's hard enough as it is. This thing here, this constant, is just some missing value that I don't know. So I'm going to rewrite it. I'm going to rewrite it as the ln of a, which is still a constant that I don't know. Now, why have I done that? Well, because what I can now do is wrap these two terms up into a single term, and it just makes that right-hand side a little bit easier to deal with further down the road. So what I've done is replace the constant. You'll know I didn't do that in the previous question, and I didn't have to do it here, but it just is going to make it a little bit easier. What I can then do is use the first log rule, the log of a plus the log of b is equal to the log of ab, to write that. And the a sort of gets pulled into the modulus sign. So if I hadn't done that, in a minute when I e both sides, I'd have 3 terms, e to the power of something with 3 terms in the power. Now at least it's only 2, and it gets easier further along as well. I'm going to e both sides now. And I remember that when you multiply powers of the same thing, you add the indices. So this is indices being added, so that must have come from this. And e to the ln of something, they cancel each other out. So I end up with, sorry, my minus sign is getting a bit lost there, isn't it? But that's still a minus sign. So this just becomes ax, no modulus sign, and I've just chosen to write it in front, just so it looks a bit prettier. So that's an alternative general solution. This was also a general solution, but it wasn't in the form y equals, which is what they asked for, and I was going to have problems when I substituted in my boundary condition. Now, it's a whole lot easier to substitute in the boundary condition. Y is e to the power of 4, x is minus 1. Go on, have a go, see what you get.
So I'm confused.
Where have I lost you? A, it is confusing. It's rock hard. Okay, so you're probably doing it right if you're confused. Yeah.
I thought when you put an e into an ln, it just gets with the ln.
They cancel each other out. So it's like me asking you, what is 5 squared square rooted? It's 5. So here we've got a to the x, ln, and then e. So we get back to a to the x. So that whole thing just becomes that.
Right. So it just turns into times ax rather than...
Yes, well yes, so it's that times that, isn't it? So I could have written it as e to the minus x times ax, I just chose to write it. So just see if you can substitute those values in. we're wanting to find A. The constant is A now, isn't it? Not C. We can call the constant whatever we want. Minus 1 over minus 1. So if I divide both sides by e to the power of 1, a is minus e cubed. So my particular solution is minus e cubed x e to the minus 1 over x, which looks weird and funky, and you could combine these two together as e to the minus 3 over x, but yeah, I'm just going to leave it like that. That's my particular solution. If we had substituted the values into the general solution in this form, we would have got plus e cubed x e to the minus 1 over x, which is wrong. And I know because I spent about 2 hours yesterday trying to get my head around why I was getting the wrong answer to all these questions. So, this is the problem. At this point here, I realised, right, that's going to cause me a problem. I've got to make sure that I do that extra step instead. Look at that. Goodness me, time flies when you're having fun. We will pick this up tomorrow.